So let me give a couple examples of torque in application right here. So one example is you have a helicopter. So imagine you got a helicopter, you got the blades here, and you got the body of the helicopter, and so as the blades are turning around here, then what's happening is that the blades are turning, but there's air resistance. So the air resistance is pushing on the blades. So that means that the motor of the engine of the helicopter has to exert a torque, because if you've got something that's rotating and you're pushing back, that's exerting a torque on it. So you have to exert a torque to keep it going. Now, remember, torque equals R times F times sine theta. Because every force has an equal and opposite force, every torque has an equal and opposite torque. So that means there's a torque on the helicopter. So that means as you're pushing on the helicopter pushes on the blades, then the blades push back on the helicopter, and the helicopter tries to swing to the side. Okay, so how do you keep it from doing that? Well, you put a small rotor at the back end of the helicopter that exerts a force in the other direction, and that provides a torque opposite to the torque on the rotor, on the main rotor. Okay, so in that case, why does this tail rotor, why is it so much smaller than the main rotor? Because R is bigger. And so you don't need as big of a force. Well, compare this to the military's big Chinook helicopters. Okay. So here we have a Chinook. There's no tail rotor. So what keeps it from torquing around and spinning? Well, if you actually look carefully at the main rotors, they rotate in opposite directions. So one of them is going one way while the other is going the other way, and therefore the torques cancel out. If you imagine a single engine aircraft, so this is a P51 Mustang from World War II, and so the engine drives a propeller up front, so the propeller is turning. Again, there's air resistance in there, and that air resistance tries to slow the propeller, so the engine has to provide a torque to keep it going. That torque pushes torque back on the aircraft, and so that means that the aircraft now wants to twist in the opposite direction. So as you're trying to turn the propeller, as you're trying to turn the propeller this way, the aircraft tries to turn that way. And so you have to compensate for that. And of course, that's part of what the empennage does at the back end of the aircraft. As you're going forward, then that resists that kind of motion. But if you're turning the aircraft, remember, you've already got torque here, and you turn it, you induce more torque. And so that means that when you're turning, then this extra torque tends to try to twist the entire aircraft a little bit. And so therefore, you would have to adjust the empennage surfaces back here to compensate for that. If you're otherwise, you end up going in slightly different flight than you'd slightly different direction than you want to go. P38 is another World War II aircraft, and the interesting thing here is that you have starboard and port engines that were actually going in different directions. And so that means the torques averaged out. And so this was a no torque flight, no torque aircraft, and so that actually made a much sweeter aircraft to fly. They were much easier to fly, and so they behaved differently. So you didn't have to worry about the same sort of things. So people pilots that were used to flying in twin engine aircraft of this sort, when they transitioned to the P51, they sometimes crashed until they got used to flying the single engine aircraft, because twin engine aircraft, particularly if the twin engine aircraft have contra rotating propellers, behave quite differently when you're maneuvering, when you're climbing or turning, than a single engine aircraft would. And part of this has to do with the torques.